Hello, welcome to everyone to this new tutorial of Copernicus products. In this session we are going to make an analysis of the emissions and air quality impact from forest fires. This tutorial is presented in the framework of the WEkEO training workshop for forest monitoring. And my name is Álvaro Pascual Collar. I am oceanographer in Now Systems, and this tutorial is presented in the format of Jupyter notebooks. Well, going directly to the contents of the course, here we have the Jupyter Hub where we have installed the tutorial Training Forest Monitoring 2024. And here we have the file IPyNV, the Training Forest Monitoring 2024, that we can open by double clicking on it. And here we have the notebook. For those of you that are not familiar with this notebook format, I will tell that these notebooks contain a mixing of documentation, like you can see here, and this documentation is pretty similar to the documentation or the text you can find in any web page, and also it contains some cell codes like this one that can be run by clicking on this run button up here, and also can be run by pushing the keyboard shortcut Shift Enter and Control Enter. For example, we can run this cell by pushing Control Enter, and as you can see here appear an asterisk, and after when the cell is already run, there appear a number that indicates the identification number of this execution. Well, but starting the tutorial from the beginning, as I said before, in this tutorial we are going to assess the emissions of air quality impact from forest fires. And in this tutorial we are going to cover the following sections. First of all, I will give you a very short introduction to the topic. After that, we will learn how to access the Copernicus data by WEkEO. Here in this section we will explain how to download data from the Harmonized Data Access API, and we will learn how to open NetCDF files, and we will learn what objects we can find in NetCDF files and how to work with them and access the data. And after that, we will start with a very simple exercise that will learn us how to plot any variable in NetCDF files. In this exercise, we will make a visualization of the average climatic values of the files we are working with. And after that, we will start to analyze specific events of wildfires. We will focus our interest in a specific event, and after that we will learn how to compute the average values of air quality during a specific forest fire. And to finish in the tutorial, we will learn how to compute the anomaly values of air quality variables during this period of wildfire. And at the end we will have some conclusions. Well, as you know, wildfires has lots of impacts, socioeconomic impacts, but one of the impacts that can have the wildfires is the emission of huge amounts of different pollutants like carbon monoxide, nitrogen dioxide, nitrogen monoxide, carbon dioxide, or even particulates like PM 2.5. In this tutorial, we are going to focus our attention in some events occurred in the Iberian Peninsula, for example, in Pedrogal, which is a region in Portugal. There was a wildfire in 2016, and also in Spain, in Losacio, in 2022. And also we will learn how to translate this tutorial to the case of a wildfire in Greece, in Alexandropoli, in 2023. Well, this tutorial is presented, is designed to be run twice. And this is because we are presenting this tutorial using two different Copernicus datasets. We are going to use a global reanalysis of air quality from CAMS, and we are going to use global biomass burning emissions based on fire radiative power. These two datasets are quite similar since they are related with air quality and emissions, but the first one is the result of air quality from our analysis. So it's not exactly the same than the data set of emissions based on fire radiative power, right? So this tutorial is designed in order to be run twice. So you can run first the tutorial using the global reanalysis data and see the results, analyze the event, a specific event of wildfire. And after that, you can run again this tutorial using these global biomass burning emissions. And well, you will learn that despite of the results are very similar, since these two datasets are not equal, they will give some different information in any case. Well, later we will explain a little bit better how these two datasets, the two datasets we are going to use. And here we have the first cell code we have in our notebook. This cell code, it's very common cell code in Python language. Is the first cell code is devoted to configure the environment you are going to use. In this cell code, you have the list of libraries you are going to use in your script. As you can see here, we are going to use this list of NumPy, XRI libraries, and every time we are going to refer a function inside these libraries, we are going to use this alias np, xr, or mpl, for example. You can see here we have the list of libraries we are going to use, and here you have the links to the main documentation page of any library we are going to use, so you can expand the information of this tutorial, learning a lot about the functions included in these different libraries. As you can see here, we are going to use these NumPy and XRI libraries that are mainly associated with numerical computation, and also XRI also provides a lot of functions related to access the netcdf format files. And we are going to use also Cartoby and Matplotlib, that are two libraries for plotting and for creating maps and geographical maps with geographical projections, etc. And we are going to use also this library, HDA, which is the library of the harmonized data access. This is an API that allows users to easily download data from WEkEO platform. We are going to learn how to use this API to download the data we will need for this tutorial. Well, starting with the first section, or the next section of this tutorial, here we have the two datasets we are going to work in this tutorial, the CAMS global reanalysis and the global biomass burning emissions based on fire radiative power. This is a reanalysis product. This one is a reanalysis product, and this one is a product obtained from teledetection, from satellite. And as you can see here, we have the identifier, the product identifier of both products, and we have the link, so you can follow this link to go to the documentation page here in the data viewer, so you can expand the information you have. You expand all the information you need to learn about these products, and also you can navigate through these products in the data viewer. Well, from these products, we are going to download the same dataset, 11 years from 2013 up to 2024. We are going to download data, daily data at 12 hours. We are going to download also a window focused or centered in the Iberian Peninsula between these boundaries of latitude and longitude. And as you can see, we are going to download different variables related with air quality. Here we will download the total column, carbon dioxide, nitrogen dioxide, nitrogen monoxide, and sulfur dioxide. And here in this other product, we are going to download data related with the wildfire flux, which are emissions of carbon dioxide, carbon monoxide, nitrous oxide, and particulate matter, PM 2.5. Well, the first thing we are going to do in our code is first defining some parameters that will create some variables that will be constant, so we can use it in different locations in the code, and we do not need to repeat these values of variables. For example, here we have a start date and end date that correspond with the dates of starting and finishing the downloading data. And we are defining the region or study region that, as I said before, is centered in the Iberian Peninsula. Here we are defining a variable data path where we are going to download, store our data, and this variable working data set will define the data set we are going to work with. As I said before, we are proposing this tutorial in the way that you can run twice this tutorial, and we recommend to run first this tutorial using this global reanalysis data, and you can get the same conclusions and etc. But once you have downloaded it, you have run this first tutorial, you can download again a new data set, so you can run again this tutorial using a different data set of the emissions based on fire radiative power, so you can get different conclusions, because, well, since these are data of emissions related to wildfires, you will get a similar result that in the previous case in the reanalysis, but well, more focused on the emissions, right? So with this variable, we are defining for the rest of tutorial what dataset are we going to work. In this case, we are using the air quality data, and in the case of CAMS EM variable, this kind variable is equal to CAMS EM. This will be associated with the emissions dataset, right? So, as I said before, we can run this cell by selecting the cell and clicking on this run button. And once we have defined these parameters, we can start working on downloading data. To download data from the Harmonized Data Access API, first of all, we need to configure the client, including the credentials in a specific file like this one called .hdarc. So this is the proposal of this cell code. So we can run this cell code and it will ask us about our credentials. We can run this cell by clicking in the run button here. Well, this has skipped this situation because I already had these credentials defined. I will remove the file . Well, and we can continue with this cell. Sorry for this. Well, here I am asked for the username of my Copernicus account. I will put the username and the password. Oh, when you have defined this file HDRC, you can access to the harmonized data access library. So you can use these commands to download any data you need. As you can see here, these commands related with HCDA depends on a request, and we have to configure this request, and we are going to do that in this cell here. We have two different requests stored in a tag dictionary. As you can see here, we have this dictionary that has the CAMS air quality, the request associated to the dataset of CAMS air quality, and the request needed for CAMS emissions. You can see here this request contains another dictionary, that is this one, with different parameters, for example, dataset ID, start date, end date, time, variable, the name of the variable, DB box, boundary box, and the format of the file we are going to download. So you need to define these parameters to configure a successful request, right? These parameters can be obtained from this data viewer. Here you have the way to access these parameters. So you will learn in the data viewer what is the identification ID, the dataset ID of the product you want to download, or etc. The parameters you need, for example, here. Well, so then you can run this cell. And since we have previously defined the working dataset as in the previous parameter as CAM air quality, you can see here we have a request. We are displaying a request that corresponds to the request of the reanalysis data, air quality reanalysis data. Well, and once we have this request, we can go to use the harmonized data access API by using these functions. For example, the client function initialize the HCDA client, and with this we are making a search inside with this function HCDA client search. We are making a search of the request we have previously defined, and after that we can download. Once we have some answer from this search, we can download this answer by using this function matches.download. I am not going to run this cell here because this will take some time to run. Maybe we can just try to comment this downloading process and try to get the matches of our request. We can run the cell, and despite of it takes few seconds, you will realize that we can print matches, and the system has found one item, and after that we could download this item using this function matches download data path. As I said before, I'm not going to do this. I'm not going to run this instruction now because it can take some time. So in this case, in this tutorial, we have here in the folder data, we have already downloaded the products we will need for this tutorial. So we can continue with the tutorial. You can run this cell and you will realize that the downloading is successful in few minutes. Once we have already downloaded the data file, you will realize that this previous sol downloads a file with extension .nc. These are netcdf files, and well, there are also the xarray function from Python. Provides a lot of different functions devoted to access the netcdf files. So we can use this open dataset file, open dataset function to open a file that we have called file name. Here you can see that this file name is a summation of the path where the file is and the name of the file. And here we have again a dictionary that defines the name of the file depending on the dataset we have already defined. Previously defined. Since our working dataset is scans air quality, the name of our file to open will be this one. And if we could change this working dataset in the previous parameter, we would open this emissions file, right? Well, we run this cell by pushing Ctrl-Enter. And here you have, since we have this instruction displayed yes, you can see that this xarray open dataset function creates an object that we have called ds dataset, and this dataset is used as a kind of pointer, so we can access the data inside the file by using this pointer. For example, if we use the function display over the ds object, we will get this report where we can see the different objects and the sorting report of the information stored in our dataset. For example, here, for those of you that doesn't know about the objects that can be found in netcdf files, you can see that these netcdf files have three different objects that are variables, the dimensions and coordinates, and also attributes. For example, variables are the multidimensional arrays where we have the data. For example, here, looking at this report, we can see the file we have already opened has four different variables. These ones with this name on the variables. This is a name, and by clicking on this page, we can open the attributes, the variable, and we can see the different attributes associated to these variables. For example, here we have many graph attributes, but we also have interesting information. For example, the long name gives us the total, the name of this variable. So now, since we have this long name, total column carbon monoxide, we know that this TCCO variable is the concentration of, no, it's not a concentration, it's the total column carbon monoxide here. And for example, if we open another variable like this one, we can see the long name, the total column sulfur dioxide, right? We can also access, there is also some similar things like variables are the dimensions and coordinates that are here, that usually are one-dimensional variables that contains the information of the different dimensions of the dataset. Here you have defined three different dimensions on this dataset. We have valid time, latitude, and longitude, and in these coordinates we have the values of these three dimensions. For example, it's interesting to go over the valid time. We have here the information of the long name, time, and standard name, time. But if we click on this drive, hard drive, we can see a report, a short summary of the values we have in this variable. So here we can see that we have elements for 2013 starting at 00. No, it's not starting at 00. It's starting at 12 p.m. of January 1st, January 2013, and we have daily data up to the end of 2023 here, right? Well, we can collapse this, and we can, since we learn how to access, well, this is the basic information of the data set we have. We also have another type of objects inside the file, which are the attributes that are kind of header of the file, that where we can find interesting information, like, for example, the institution that has been created, the file or the convention we are that has been used for compiling this file, right? Well, once with this, we have already opened this data set, and well, we have some access to the data, but the best way to accessing data on this data set is by using Python commands. And so that we are going to learn how to access the data, and we are going to learn how to make a simple plot of the data stored in the data set, right? So we will learn how to plot these variables. Well, to do that, we are going to jump to the next section, which is a visualization of average climatic values. We are going to make a plot of this, of the average, of the temporal average of these four different variables. So we will get a basic information of what is the expected field of different pollutants in the region we are working on. And to do that, first of all, we will need to compute the mean of the variables stored in a specific dataset. So to do that is quite simple. We just need to use the function mean. This is an XRI function associated to all XRI datasets. So we can we can use this instruction ds.mean, and we need to define the dimension along which we want to compute the mean. So with this, we are creating a new XRI object mean. We can run this cell, and as we can see here, we have displayed this created object including the mean, and here you can see that despite of before we had the time dimension in our dataset, the new object created doesn't contain time dimension because we have removed this dimension when we have computed the mean, right? So right here we have a flat element with latitude with only two dimensions, latitude and longitude, and we can plot this element, or we can plot this array as a map, right? So we can go to the next cell code where we are defining a plotMap function, and with this plotMap function we are going to apply this function to create the map. Just allow me to run this function, and I will explain the result while it is running and also having the result. Well, when we run this cell code, we can see that we have created a map of the mean total column nitrogen dioxide in the Iberian Peninsula, in the region of the Iberian Peninsula. You can see here this pollutant is strongly associated to the emissions associated of the traffic in cities and the industrial activity, for example, here and here. And well, to plot this map, we have previously defined this function, plotMap, and after that we have used or invoked this function to plot a map, right? In this plotMap, we have included all the code lines we need to plot a map of any variable. Here you can see we have different functions from matplotlib and cartby. functions devoted to add the coastlines to the map, for example, and remove latitude levels in the right side of the map, or we are formatting of XRI, X-axis and Y-axis, adding or removing the land mask, the country borders, etc. And we are using this function pcolor, which is a matplotlib function. It's called pseudocolor. This pcolor function allows us to create a pseudocolor plot of any array. So we have to give to this function the information of the data in the x-axis, data longitude, the latitude in the y-axis, and also the variable we want to plot, and the name of the color map we want to use. And with this function, we can create a map like this one, a pseudo-color map, because we are associating every value of the array with a specific color in the grid, right? And here we have also some final editing commands in the function. Here, for example, devoted to add the title to the figure, the color bar, and format the ticks, and format the color bar, etc. Right? So here we have, once we have defined the function, we start running the code itself. These first lines of code here are associated with a new dictionary where we are defining a default variable to work with, depending on if we are using CAMS air quality or CAMS emissions. We are going to define the name of a variable to work by default. This is the name of the variable we are plotting here. As you can see here, we are working with the name, the alias of the variable, the name of the variable that was found here in the report of the dataset. We have these short names, so we have to work with these short names for when we are accessing the data. Well, when we are using this, we are going to define some, using these two lines, these two instructions, we are creating a figure object, fig, and an axis object. This is needed in Python to make any plot. You need to create the figure and the axis, and you can plot anything over the axis, right? So when we call the plot map function, the different parameters that we are passing to the function is the axis where we want to plot, make our plot, and the data, the data set we are going to work with, and the variable var name inside the data. So the function accesses the information of this data set, accessing the information of the longitude and latitude data, and also accessing the information of the variable we have defined it to be plotted here as var name, that in this case, this var name corresponds to the variable associated to the dataset we are working with, right? So we are, in this case, since we are working with CAMS air quality, we are plotting this TCNO2 that correspond to nitrogen dioxide, total column nitrogen dioxide, right? So this is our result, as I said before, strongly associated to the cities and the traffic and the industrial activity in this case. But well, this is interesting, but it would be also interesting to see the different variables, right? We could run this plot map function different times to run the function using the different names of the variables. But well, we can also try to make a plot that contains different panels, and including in each panel the information of one variable. And to do that is what we are going to do with this new plot function that we have defined, plot air quality. And for this air quality, the parameters that are pasted to this plot AQ is the dataset we are going to use, and also the function to plot we want to use. The plot function we are going to use in this case is this plot map function that has been previously defined. So this function, plot air quality, is going to create an array of different subplots in this figure. It's going to create a figure with different axes, and in this axis is creating a figure with different panels, in this case organized with 2 rows and 2 columns, for example, number of rows and number of columns. And we are using also the a specific projection, because we are going to plot a map, right? Maps in these panels. So after that, we have this iteration, a for loop, where we are going to use the plot function. In this case, the plot function is going to be plot map. So we are going to use the plot function to create a map inside this axis index, right? So we can run this function, and with this function you will realize that we are using this previously defined plot map function to create a new map included as a panel inside a main figure, right? So with this we can have a quick view of the different variables we have in our dataset: carbon monoxide, nitrogen dioxide, nitrogen monoxide, and sulfur dioxide. You can see here, but well, this is a good way to present the information, a compact way of presenting information. But well, we said in the beginning of this tutorial that we are going to focus this tutorial in the analysis of wildfires, but until here we haven't talked about wildfires. We are only presenting the information, the basic information of how to plot the information of different variables. From now on, we are going to focus on the specific events of wildfires, and we will learn how to apply these functions we have previously defined to study the specific events of forest fires. In this section, we are going to learn how to visualize the average values during a forest fire. Here we have a cell code where we have defined a new dictionary associated with 2 dates. For example, the event of Pedrogao, we have the information of that started, this wildfire started in 2016, then July, 16th of July, and it was extinguished in 24th, right? This is the period where this Pedrogao event occurred, and we have also the event of Losacio. This event started in July 2022, and finishes in August, at the end of August of 2022, right? So with this, we are going to define a new parameter that is the study wildfire. With this parameter, we are defining what event are we going to study. In this case, I am going to study the Pedrogao wildfire, but you can change this selection by commenting this line, and uncommenting this one. So since the study wildfire is Losacio, this tutorial will continue applying the study to the Losacio event, right? Using this range of dates. But well, in my case, I am going to select this Pedrogao event, and I'm going to run this cell. If here. Well, with this, we are just defining this initial and finishing date for the event of the wildfire. And from here, we want to compute the mean values of the air quality variables during the forest fire, right? So in this new cell code, I am going to compute the mean of the different variables during the wildfire period. So to do that, I am going to use a new function from XRI, very useful function called cell. This cell function allows us to select specific indexes inside of a dataset. So with this cell function, I am selecting the specific values of valid time. This is the name of the dimension we are selecting, including the slice from date ini to date end. As you remember, we have defined date ini and date end right here. So with this instruction, we are selecting the group of data that meets that the date dimension is between these two starting and finishing date. And once we have selected the data we want to use for our mean, we can apply after that the mean function, a function that has been previously used in the previous section. And using this function, we are computing the mean during this specific period along this valid time dimension, right? We can run again this cell by clicking the run button. And you can see here we have again a new wildfire mean, a new object that contains information of the four variables, but including just latitude and longitude, because we have here the mean computed in this period, only including this period, right? And since we already have this plot air quality function that allows us to plot all the variables stored in a dataset, we can use this plot air quality function to plot the result of this wildfire mean using the function plotmap. We can run this cell and we will get the result. And as you can see here, we have the mean value of the total column of these four pollutants computed during this period of the Pedrogao wildfire. As you can see here, in the result, we can see the very high values of these different pollutants in this region of Portugal. Pedrogao is located more or less here between 8 degrees west and 40 degrees north. It's more or less like here. So in these cells of the grid, we have very high values of these pollutants. And well, this is interesting, but for example, here the signal in the case of sulfur dioxide is not very clear. So, well, this is an interesting tool of computing the mean value during the period, during the event, but maybe it's not enough to define or to locate the event. And so we can refine our analysis by computing the anomaly values during the forest fire. Well, statistically, the anomaly is defined as the difference between the variable and the mean of this variable. So to compute anomalies, we just need to compute this difference. The variable wildfire mean that was previously defined, that was previously computed, minus the climatic mean, right? So we can run this cell, and with this we have the anomalies of this event. And to plot this, we could use also the plotmap function and plot these result, as in this case with a rainbow color scale. But for this case, for plotting anomalies, it's more interesting to use a color scale that starts with blue, goes to the white, and after that the higher values are plotted in red colors. So the zero value is located associated to the white. Just let me run this cell so I will explain you this. As you can see here, we have created a new function that has been called plot_anom_map, and with this plot function we have defining the same map than before, exactly the same map than before, but we have changed the color scale. So the negative values are associated to blue colors, and the red values are associated to red colors, and in the middle, in the zero, is associated to white. So we can get darker values when we are farther from the mean, that in this case is the zero, right? So we get this kind of maps where it's very simple to define with what regions are associated with values below the climatic mean, that are the negative values, and the regions that are above the climatic mean, that are the red ones, right? How have we done this? Well, we have defined it to do this. We have defined this plot_anom_map function that, as you can see, it's almost the same function that just before, but we have included this instruction that define the limits of the color scale, defining the absolute maximum in the data we are going to plot. Here we get the absolute value of this data, and we get the maximum, so we can define the color scale, the limits of the color scale, according to this limit, from minus CMAP limit up to CMAP limit plus CMAP limit. So we are defining this color scale, these limits of the color scale, and also we are using a different color map. Before we used the rainbow color map, but right now we are using this color map that is this blue, white, red color scale. So this is the only difference with the plot_map function, previously defined plot_map function. The rest of the instructions in the function are exactly the same than before, and also we are using the pcolor function, the pseudo-color map, to plot the results, right? And we apply this plot_anom_map to the axis that was previously defined here, including the projection, because we need to include a projection because we want to plot a map with a cartographical projection, right? So we have to define the axis, defining the specific cartographical projection. And we are defining as parameters the axis where we are going to plot the map, the array, the data set we want to plot, and the variable inside the data set, right? Just like before. And once we have this plot_anom_map function, we can use again the plot_air_quality function using this plot_anomaly map function. So with this, we are able to use this plot_anom_map function for all the variables. And in this case, yes, you can see that right now, yes, we have a very clear signal of the wildfire of Peruel here, and also in the sulfur dioxide image. Well, this is the end of the tutorial. In this tutorial, we have learned how to use the HDA API to download these two products from WEkEO, and we have learned how to access NetCDF datasets, and we have learned what kind of objects can be found in NetCDF files, and how to access to these objects and work with them. We have learned how to plot maps of any variable. Actually, you can apply these functions to any variable of almost any product, any Copernicus product. And we have learned to create a figure containing multiple plots, including different panels inside a figure. We have learned how to compute temporal means of niche files and also specifying the range of time of dates to be included in the mean. And also we have learned how to compute anomalies for all the variables in a data set, right? Well, as final exercise here, as I said before, we have no time to run again this tutorial for the second data set, but well, as I said before, this tutorial is designed to change this parameter here in this cell, so you can run again this tutorial using the emissions file. Using the emissions file, so you will get a different result, and you can try to analyze this event of Pedro wildfire from the point of view of the emissions associated to the wildfire. And also we are proposing a very different final exercise. If you want to fight with this topic you are interested in, we are going to propose you a new exercise. You can try to do it by yourself, and we propose to repeat this analysis, the analysis of this tutorial, focusing in a different region of the world and in a different wildfire. If you know any event of wildfire in any place of the world, and preferably in the period included in the datasets we already have, from January 2013 up to December 2013. You can try to analyze that wildfire, but since we can propose to analyze the wildfire occurred in Alexandropoli in Greece, in a region located near this latitude and longitude, and it was an event of a wildfire event that occurred in this period from August 21 to 28 in 2023. It was a huge wildfire. So we propose you to change these sections in the accessing data. Here we give you some information. To simplify this exercise, you can go to this accessing data section to modify the window we are using for our analysis, because right now we are not focusing on Iberian Peninsula. We have to jump into the Greece region. So we need to download data from a different region of the world. And also you have to include in the period, in the code, you have to include the period of this Alexandropolis wildfire. So, well, I hope you find a way to do this exercise. And well, this is all for today's video. I hope you find interesting information in this video, and you find it interesting, and you find functions that you could use in your day-to-day work. Thanks for watching. I'll see you in the next video.